Hello everyone, welcome to Manmaker. I am Ranjan Kumar Kalindi and today we are going to discuss about BL fixed tenure engineer. We are going to discuss today electronics engineering important question. These all questions are expected you can say, and we are going to discuss all the question with details explanation. These questions are from your syllabus and this is your exam pattern based question. Okay. So, for PDF and more updates, you can join our Telegram channel. This is my Telegram channel name. You can directly go to your Telegram and search this name. You can join this one. Otherwise, directly link will be there in description box. Just go there and join this channel. Here you will get PDF notes and class update, everything. Okay. So, we'll start from question number 1. In which region transistor act as an amplifier? So there are four type of region will be there in transistor. If we talk about transistor region, then we have four type of transistor region. First one is cut up region, then saturation region, then active region. Active region is also called linear region. Okay, then reverse active region. Okay, four kind of region is there in a transistor. And when this regions will work, how it is work in biasing, like when junction emitter to base junction and collector to base junction. If emitter to base junction and collector to base junction both are in reverse bias, then it will work in a cut-up region. Okay, and when both are in forward bias, then transistor will work in a saturation region. When emitter to base junction is in forward bias and collector to base junction is in reverse bias, then transistor will work in a active region. Okay, and when this is in reverse bias, means emitter to base junction is reverse bias and collector to base is a forward bias, then in this case transistor is work in a reverse active region. Okay, so this condition you have to remember. From here also question may came. Okay, so this is about your transistor region, in which mode they will work, means which biasing they will work in a transistor region. Suppose in a question it will come like, if emitter junction is a forward bias and collector to base junction is in a forward bias, then which region transistor is working. So you have to give a answer in a saturation region. So like that question may come. Okay, apart from this application, now in different region application is there for a transistor. Like in a cut-up region, transistor work as a off switch. Okay, and saturation region it is work as a uh, on switch. In active region it will act as a amplifier. Okay, and in a reverse active it will be attenuation. Okay, attenuation for a signal. So this is the application for all the region. So here they ask, in which region transistor act as an amplifier. So amplifier in active region it is working. So option A is the right answer. Okay, so you have to remember all these points. Now, a copper wire is 3 meter long and has a uniform cross section of 0.6 square mm. At room temperature, the resistance of the wire is 0.183 ohms. What is the resistivity of the material? So, resistivity means what? Rho. Rho is what? Rho is, R. If you see the formula for R resistance is what? Rho L by A. Okay, this is the resistance formula, and this rho is called resistivity. So we can write from here rho equal to Ra divided by L. Okay, where this L is what? L is length of a wire, A is cross section area, and R is resistance. So R we know the value of R. Resistance of a wire is how much? 0.183 ohm. and area, cross section area is given 0.6 mm square and millimeter square, and area given, then length is how much? Length is 3 meter. Okay, so now we can solve this one. 0183 into 0.6 into, we can write this thing 10 to the power minus 6, and this is 3. So we can write this thing 0.2, or this will come, if you calculate this one, so it will come how much? 0.0366 into 10 to the power minus 6 ohm meter. Okay, or we can write 3.66 into 10 to the power minus 8 ohm meter. Okay, so from here option B will be the right answer. A diode, when connected in a series with the output, the circuit is called. Okay, so when a diode is connected in a series with the output, so we have clipper circuit. Okay, we have clipper circuit. When diode is connected series with the output, then it is called series clipper. Okay, and when diode is connected parallel, okay, when it will connect parallel, then it is called parallel clipper circuit. Okay, again it is divided into two parts: positive series clipper and negative clipper. Okay, this is a positive parallel clipper and negative parallel clipper. Okay, so when diode clipper circuit means what? Clipper circuit is a circuit which is used to clip a half cycle, positive half cycle, or negative half cycle, or both positive or negative half cycle, they will clip. Okay, so clipper circuit connected series, so it is what? Series clipper. Option B is the right answer. Okay, which region cover the highest area in a transistor? Okay, if we see the structure of a transistor, so there are three terminal in a transistor. Okay, one is emitter, base, and collector terminal. Okay, so if we see emitter, base, and collector, if we talk about size, then emitter size is always moderate. Okay, emitter size is moderate, base size is small, and this collector size is largest. Okay, so here they asked highest area, so highest area is covering who? Collector. So option B is the right answer. And here some more question will come about doping. They will ask sometime about doping, in which, like, what is the doping of emitter, like that they will ask, or they will ask highly doped region, highly doped area or in a transistor, like that they will ask. Okay, so in emitter is generally highly dropped. We called emitter is a highly dropped. Base is lightly dropped. Okay, base is lightly dropped, and collector is moderate. Okay, this is what? Moderate drop. Okay, so you have to remember this all point. Okay, whatever I am explaining in a solution, that points you have to remember from there also question may come. Okay, now a tuned amplifier has a peak output of 9 megahertz at a quality factor of 90. What is the bandwidth of a tuned amplifier? So we have given quality factor, they ask about bandwidth. So what is the relation between quality factor and bandwidth? Or we can say bandwidth equal to what? F naught divided by quality factor. This is the formula for bandwidth. Okay. F naught is what? F naught is frequency response. So we have given frequency how much? 9 megahertz, or we can write 9 into 10 to the power 6 hertz. Okay. And quality factor is 90. So we can write this thing 90 into 10 to the power 5 and 90. So it will come 10 to the power 5 hertz. Okay. Or 10 kilohertz. Okay, 100 kilohertz. 100 kilohertz. Option B is the right answer. Okay, and sometime they will ask question like that. What is the relation between quality factor and bandwidth? So bandwidth is inversely proportional to quality. Like that you need to give answer. What is the relation between bandwidth and frequency? So bandwidth is directly proportional to frequency. Like that you have to give answer in a resonance circuit. The phase shift between input and output of an emitter follower. So basically we have transistor configuration. So we have three type of transistor configuration: common emitter, common base, and common collector. This common collector is known as a emitter follower. Okay, this common collector is known as a emitter follower. If we talk about phase shift, so phase shift of common emitter is 180 degree. Okay, common base is 0 degree and common collector is 0 degree. Okay, so from here option A is the right answer. Sometimes they will ask a question from power gain also. What is the power gain for common emitter? So what is the power gain of common emitter is high. It has high power gain. Common base has common base has low power gain, and common collector has moderate power gain. Okay, so this is about the what phase shift between input and output emitter follower. Here it will be moderate. Okay, common base is a moderate and this is low. Make it correction. Okay, power gain of a common emitter is high, power gain of common base is moderate, and power gain of common collector is low. Okay, this is the answer. Which among the following theorem can be applied at any active or passive network? So from these option, only this option B is there, Television theorem. Television theorem is applicable, means Television theorem can be applied in active or passive network or linear network, non-linear network or time variant network or time invariant network. Okay, so this is tangent theorem is applicable for all type of network. Okay, like that Thevenin theorem is this is the answer option B. Thevenin theorem is applicable only for linear type network. Superposition is also applicable for linear network, and Norton theorem is also applicable for linear network. Okay, so this is the answer. What is the condition for the maximum power delivered for a source to its load? So for maximum power transfer, from maximum power transfer theorem, in a circuit maximum power will be transferred when load resistance is equal to a source resistance. This load resistance should be equal to a source resistance, or we can say load resistance is equal to RTH, RL equal to RTH. Okay, this condition they should follow, then maximum power can be transferred in a circuit. Okay, this maximum power transfer theorem is also applicable for maximum power transfer theorem will be applicable for linear network only. Okay, this thing also remember. Which among the following multivibrator is unstable in any state? So generally we have three type of multivibrator: astable multivibrator, bistable multivibrator, and monostable multivibrator. We have three type of multivibrator. So this astable multivibrator have zero state, zero stable state, zero stable state, or we can say zero stable state or unstable state. Okay, in a astable multivibrator. In bistable multivibrator, bi means two, so it has two stable state. It has two stable states. Okay, monostable, mono means one, so it has one stable state. Okay, so this thing you should remember. Here option A will be right answer. Find the 2's complement of 8-bit number that is represented at 28 in a decimal number. Okay, 28 we have given as a decimal. So first we need to convert this thing in a binary form. How we are converting binary form? To means any decimal number to convert in a binary form, we have to follow division method. So divided by 2, so it will come 14. No remainder means 0. Okay, so 2, this is what 7, no remainder means 0. Again 2, so 6, it will come in 3 times, so 1 will be remainder. Again 2, so 2 will be in 1 time and 1 remainder. Okay, so from like this you need to write means 1 1 1 0 0. Okay, this is the binary number, but here they told 8-bit number. So 8-bit number, this is 1 2 3 4 5. So we have to add 30 in left side. Okay, right side, sorry, left side, left side. So this is the binary representation of 28 decimal number. Now we have to convert this thing in a 2's complement. So for that, first you need to complete this thing in a 1's complement. For 1's complement, we have to make 0 in a 1 and 1 in a 0. Okay, 0 0 0. This one is 1, this is 1. Okay, like this. This is what? This is 1's complement. Okay, now for 2's complement, we need to add 1 here. So this is what? 1 plus 1 is 10. So this is 0 and 1 is carry. So 1 plus 1 again 10. So 0, 1 is carry. So 1 plus 0 is 1. Here 0, 0, 1, 1, 1. This is what? 2's complement, and this is option B is the right answer from here. Okay. Next, in digital transmission, the modulation technique that required the minimum bandwidth is. So there are generally we have three type of digital modulation technique in a digital transmission: PCM, DM, and DPCM. PCM means pulse code modulation, delta modulation, and delta pulse code modulation. So bandwidth will be maximum in PCM, pulse code modulation, and minimum in delta modulation. And DPCM, delta pulse code modulation, here it will be, you can say, moderate or less than PCM. Okay, so this thing you need to remember. Now next question: 150 ohm transistor, a 150 ohm transmission line is connected to a 300 ohm and resistance and to a 60-volt DC source with zero internal resistance. The voltage reflection coefficient at the load end and at the source of the transmission line are respectively. So we need to find what? Reflection coefficient. So reflection coefficient is what? Reflection coefficient we will represent in this symbol. This is J, and this is ZL minus Z naught divided by ZL plus Z naught. Formula will be like this. ZL is load impedance, and Z naught is characteristic impedance. So here it is given how much load impedance we have: 300 ohm minus this characteristic impedance we have given 150. So 300 plus 150 again. So it will be 150 divided by 450. So it will come 1 by 3. Okay, in a first case. Again, in a second case, they have told and to 60-volt DC source with a zero internal resistance. In this case, resistance will be 0. Internal resistance is 0. That means our ZL will be 0. Load resistance is 0. Okay, and this is 150 divided by 0 plus 150, that is equal to minus 150 divided by 150, and this is equal to minus 1. So this is 1 by 3 and minus 1. Option D is the right answer. Okay, minimize the Boolean expression. We have to minimize this thing. So we can minimize this thing using K-map. Okay, you know all K-map. So this is what K-map I am going to solve for 4 variable. 1, 2, 3, and 4. Okay. So this is what we can write A, B, and C, D like this. This is what 0, 0. This is 0, 1. This is 1, 1, 1, 0. Again 0, 0, 0, 1, 1, 1, and 1, 0. This is 0. This is 1. This is 2. This is 3. This is 4. This is 5. This is 6. And this is 7. This is 8. This is 9. This is 10. And this is 11. This is 12, 13, 14, and 15. So like this we are writing a K map. Okay. So here you can say this thing we have to write in a K map. So 0, 0 here, 1, 1 is here, then 2, 2 is here, okay, then 6, 6, 6, 6, 6 is here, then 7, 7 is here, then 10, 10, 10 is here, then 14, 14 is here. So this will be come like this we have to fill. Okay. Now D is what? This is don't care. Okay, this is don't care. So we can put 3 as a don't care, 8, 8, 8, 8 is a don't care, then 11, 11 is a don't care, then 15 is a don't care. Now we have to make pair. So like this we can make one pair here. Okay, and this pair we can make here again, and this two we can make. So this pair we can say this is what? This is A bar, B bar. Okay, and this quad octet, this group of octet 8 group, this will be what? We have to write common. Common is what? 1. 1 is what? C. So it will be C. So Y equal to what? A bar, B bar plus C. We can write the solution for this output. Output will be A bar, B bar plus C. Option A is the right answer. Okay. Minimum number of 2 is to 1 multiplexer required to design 16 is to 1 multiplexer. Multiplexer means what? Multiplexer which have many input and one output. This output will be selected by a select line. This is multiplexer. So here question is asking like we have to design 16 is to 1 multiplexer. Okay, so we have 16 input and 1 output and 4 select line. Okay, using 2 is to 1 mark. So how many 2 is to 1 marks required to design 60 is to 1 multiplexer? So like this question you need to how you will solve. This is 16, this is 2. So you have to take like this 16 by 2 that is equal to 8. This will come in a first stage. Okay. Again 8 this add you have to write 8 by 2 equal to 4. This will come in second stage. Then this 4. So 4 by 2 equal to 2. This is third stage. Then again this 2. So 2 by 2 is 1. When till 1 you have to divide like this. Okay. This is fourth stage. Now this 8, 4, 2 and 1 you have to add. 8 plus 4 plus 2 plus 1 that is equal to 15. So 15 multiplexer required. 15 2 is to 1 multiplexer required to design 16 is to 1 multiplexer. Option C is the right answer. Okay. Here you remember one thing you can note down. This is for applicable for only 2 is to 1 multiplexer. Whenever anything is given, like using 2 is to 1 multiplexer, we can design 16 is to 1 multiplexer, 32 into 1 multiplexer, 8 into 1 multiplexer. Then like that if they will ask how many 2 is to 1 multiplexer required to design 32 is to 1 multiplexer or 16 is to 1 multiplexer, then simply what you need to do, whatever you need to design. Suppose here 16 they ask, so 16 minus 1 is 15 is your answer. Okay. If they will ask 32 is to 1 you need to design, then directly 32 minus 1 is 31 is your answer. Like this you have to give answer for 2 is to 1 multiplexer. A super heterodyne receiver with a IF of 450 kHz is tuned to a signal at 1200 kHz. The image frequency is. So image frequency. Image frequency, if you see the formula for image frequency is what? Fs plus IF. Okay. Fs is what? Fs is incoming signal and IF is intermediate frequency. Okay. So we have incoming frequency how much? 1200 kilohertz plus intermediate, two intermediate. This is the formula. Fi equal to Fs plus 2If. So 2 into If we have 450 kilohertz. So 1200 plus 900 equal to 2100 kilohertz will be your answer. Option D is the right answer. Okay. Next question. The short circuit impedance and open circuit impedance of a transmission line are 4 ohm and 25 ohm respectively, then characteristic impedance equals. So characteristic impedance is equal to what? Under root Z open circuit and Z short circuit. Okay, short circuit. So here we have everything. Short circuit impedance and open circuit impedance we have given. Open circuit impedance is how much? 25, and short circuit impedance is 4 ohm. So 25 into 4 is 100, that is equal to 10 ohm is your answer, option A. Like that you will find question simply formula where they will ask question. Okay. For a band limited signal with max frequency fx, the Nyquist rate is of signal is. For Nyquist rate, it is always Fs is always greater than equal to twice of maximum frequency. Okay, and this is also called sampling theorem. Okay, this is also called sampling theorem. So here option D will be right answer. Fs should be always greater than equal to twice of maximum frequency. Now gray code for 1101 is given by. So we have binary number 1101. We have to convert this thing in a gray form. Okay. So for gray conversion, we have to apply XOR operation. A XOR B. We have to apply XOR operation. So in XOR operation, whenever we have a single high we have, then only one in a like in for XOR operation, if both is equal then it will be 0. Okay, like 0 0 means 0, 1 1 means 0. If any one is high, then output will be high. This is XOR operation. So here see, this is 1 1 0 1. This is binary format. So in binary, for conversion of gray code, this MSB you have to write as it is. So 1 will become 1. Now this here you need to apply XOR operation. 1 and 1. 1 XOR 1. 1 XOR 1 is what? 0. Then again 1 XOR 0. This 1 and 0. 1 XOR 0 is what? 1. Then again 0 and 1. 0 and 1 is what? 0 and 1 is 1. So this is your gray conversion of binary code. This is option B is the right answer. Suppose they will ask like gray to binary. Okay, it is given 1011. They have given gray, and you have to convert this thing in a binary. So how you will solve? Again you have to do XOR operation. But how you will do XOR? MSB you have to write as it is. Okay, then this output to this input you have to apply XOR operation, means 1 and 0. So 1 and 0 is what? 1. So it will be 1. Then again this 1 to 1 you have to apply XOR operation. So 1 and 1 is what? 0. Then again you have to apply 0 and 1 XOR. So 0 and 1 is 1. So see, this we got our question. So this is binary. Like this you have to convert gray to binary and binary to gray. Okay. Now the Fermi level of p-type semiconductor is, if we see energy band diagram, so energy band diagram is like this. This is what? Valence band. This is what? Conduction band. So in between it will like if Fermi level here, in between Fermi level there are three conditions for Fermi level. Okay, see, there are three conditions for Fermi level. Okay, one is Fermi level will come here sometime, and another one is Fermi level will be here sometime. Okay, so whenever Fermi level is between the conduction band and valence band, then it will be intrinsic semiconductor. Okay, intrinsic semiconductor. When Fermi level is just above the valence band, then this is for p-type semiconductor. When Fermi level is below the conduction band, then this is for n-type semiconductor. Okay, so from here p-type Fermi level is just above the valence band. Okay, this three diagram you have to remember from any part question will come. Okay, and this question you have to give the answer. For this question, just go to comment box and comment the answer, and also write like how this class is, so that I will continue the class further. I will bring some more question which will be helpful for your exam. Okay, and like that only I made 5 set of question PDF. In that you will get around 100 question in each set. Means if you cover this sets, you will cover 500 plus questions, and these questions are important and expected question for your exam. So if you want this one, just WhatsApp me on this number and you will get the PDF. Okay, so till then, if you like the video, just hit like on a button, kindly share with your friends, and if you not subscribe my channel, just subscribe the channel and press the bell icon. Thank you.